Right now, you're bathed in light from the universe's birth. You can't see it, you can't feel it, but it's everywhere. Most people imagine empty space as truly empty. That's completely wrong. Tonight we're discovering how accidental radio noise became humanity's deepest glimpse into cosmic creation. We'll trace the signal that proves our universe had a beginning. Before we dive into this invisible light show, drop a comment about what fascinates you most about space. If you enjoy these cosmic journeys, consider subscribing. These explorations are meant to be shared. Two engineers expected routine work in 1964. Arno Penzias and Robert Wilson aimed their antenna at empty sky. They found something impossible. A hiss emerged from every direction. Day or night made no difference. Summer or winter changed nothing. The signal stayed perfectly uniform across the entire sky. They cleaned pigeon droppings from the equipment. The noise remained. They checked for earthbound interference. Nothing explained this cosmic static. The temperature measured exactly 2.7 degrees above the coldest possible temperature in the universe. That's the afterglow of creation itself, filling every corner of space. This wasn't random noise. Scientists had predicted exactly this signal decades earlier. They called it the leftover glow from the universe's violent beginning. When everything started, the cosmos existed as superheated gas, so hot that light couldn't travel anywhere. Imagine trying to see through thick fog, but the fog is made of blazing energy instead of water droplets. Then expansion cooled everything down. About 380,000 years after the beginning, ordinary atoms finally formed for the first time. Suddenly light could travel freely across space without being blocked. That moment created the glow we detect today. We're seeing the universe when it first became transparent, like watching fog clear on a cosmic scale. This ancient light shows a perfect pattern. Scientists call it blackbody radiation, which means it glows exactly like a perfect heat source should. Every measurement matched the theoretical predictions flawlessly. The discovery earned a Nobel Prize because it proved something extraordinary. The entire universe once existed in perfect thermal equilibrium, like water in a bathtub that's exactly the same temperature everywhere. Space itself preserves this ancient temperature with incredible precision. The glow hasn't changed its fundamental character for nearly 14 billion years. This represents the most perfect example of thermal radiation ever discovered in nature. The universe began as the ultimate heat source. The signal appears virtually identical no matter where scientists point their instruments. This uniformity reveals something profound about cosmic origins. The entire universe began from an incredibly smooth starting condition. Tiny variations exist, but they're almost impossibly small. The temperature differences between different regions of sky amount to less than 1 part in 100,000. This near-perfect uniformity poses a puzzle. How did regions of space that could never have communicated with each other end up at exactly the same temperature? The cosmic microwave background proves that our universe possesses an underlying order that extends across its largest scales. The light we detect today began as blazing visible radiation, but billions of years of cosmic expansion stretched these waves longer and longer. What started as brilliant fire became invisible radio waves. This stretching effect happens to all light traveling through expanding space. Scientists call it redshift, and it's like cosmic waves getting tired over incredibly long distances. The original radiation had temperatures of thousands of degrees. Expansion cooled it down to just 2.7 degrees above absolute zero. That's colder than anywhere on Earth. Every photon in this background has been traveling toward us since before the first star ever formed. This radiation acts like a fossil record of the early universe. Just as paleontologists study ancient bones, cosmologists study this primordial light to understand cosmic history. The information traveled to us across nearly 14 billion years without being corrupted or destroyed. It preserves conditions from when the universe was only 380,000 years old. Nothing else gives us such direct access to these ancient times. Stars, galaxies, and planets all formed much later in cosmic history. The cosmic microwave background represents our deepest archaeological dig into the past, reaching back to cosmic infancy itself. Penzias and Wilson never intended to discover the universe's birth glow. They were trying to eliminate background noise from their radio astronomy work. Instead, they stumbled onto humanity's most important cosmological find. Their discovery revolutionized our understanding of cosmic origins. Before 1964, competing theories existed about how the universe began. This observation settled the debate decisively. The Nobel Committee recognized their work as one of the most significant scientific breakthroughs of the 20th century. Two engineers looking for peace and quiet instead found the echo of creation. Sometimes the most profound discoveries happen when scientists aren't actively searching for them. This discovery demolished the steady-state theory of the universe. That competing idea suggested the cosmos had no beginning and looked essentially the same throughout time. The cosmic microwave background proved the universe definitely had a hot, dense beginning. No steady-state model could explain this uniform radiation field filling all of space. Alternative cosmologies couldn't account for the precise temperature, the perfect uniformity, or the blackbody spectrum. Only the Big Bang Theory predicted all these characteristics correctly. One observation effectively ended decades of debate about cosmic origins and established modern cosmology on firm observational ground. Modern satellites have measured this cosmic temperature to extraordinary precision. The average temperature throughout all of space equals exactly 2.725 degrees above absolute zero, with incredible accuracy. This measurement represents one of the most precisely known constants in all of physics. Scientists have mapped tiny temperature variations across the entire sky with unprecedented detail. These precise measurements reveal the universe maintains nearly perfect thermal uniformity across distances of billions of light years. Such precision suggests fundamental physical processes operating at cosmic scales. The temperature measurement provides a cosmic thermometer that reads conditions from the universe's earliest accessible epoch. Looking at this radiation means literally seeing the past. The light has traveled for so long that we observe the universe as it appeared 380,000 years after the beginning. This represents our earliest possible direct observation of cosmic conditions. Before this moment, the universe remained opaque to light. After this moment, stars and galaxies began forming. We're witnessing the cosmic transition from primordial simplicity to the complex structures we see today. It's like watching a baby photo of the entire universe. No other astronomical observation gives us such direct access to cosmic infancy and the physical conditions that prevailed during universal childhood. This discovery launched the era of precision cosmology. Scientists now use cosmic microwave background measurements to determine fundamental properties of the universe with extraordinary accuracy. These observations revealed the universe's age, composition, and geometry. They showed us how much ordinary matter exists, how much dark matter fills space, and how fast cosmic expansion accelerates. The cosmic microwave background transformed cosmology from philosophical speculation into experimental science. We can now measure cosmic parameters to within a few % accuracy. Modern cosmology rests on this observational foundation, making the cosmic microwave background humanity's most important window into universal origins and evolution. The universe began as the ultimate furnace. Everything that exists today once crowded together in a space smaller than an atom. The temperature reached levels that make the sun's core seem freezing cold. In this primordial fireball, matter and energy existed in perfect thermal equilibrium. That's like having a pot of soup where every drop is exactly the same temperature. Nothing could be hotter or cooler than anything else. This state lasted for the universe's first few 100,000 years. Every particle constantly collided with every other particle, sharing energy perfectly. The cosmic soup maintained absolute thermal democracy. This primordial furnace created the conditions that would eventually produce the cosmic microwave background we detect today. Cosmic expansion doesn't just make space bigger. It actively cools everything inside that space, like stretching a rubber band makes it feel cooler to the touch. Scientists call this adiabatic cooling, which means the universe loses heat without actually losing energy to the outside. As space expands, the same energy gets spread over more volume, so temperatures drop steadily. The cooling follows a precise mathematical relationship. Temperature falls in proportion to the square root of time. This means the universe cooled fastest during its earliest moments, then more gradually as expansion continued. Adiabatic cooling transformed the blazing cosmic furnace into the cold, dark universe we observe today. Hot objects glow in a very specific pattern. Scientists call this a Planck distribution, which describes exactly how much light gets emitted at each wavelength. It's like nature's perfect recipe for thermal radiation. The early universe followed this perfect recipe exactly. As expansion cooled everything down, the light pattern kept its shape but shifted to longer wavelengths. Imagine a musical chord played at lower and lower pitches while maintaining perfect harmony. This preservation of spectral shape proves the early universe maintained thermal equilibrium throughout its expansion. Nothing disturbed the perfect balance between matter and radiation for hundreds of thousands of years. The cosmic microwave background still shows this perfect Planck distribution today, stretched by billions of years of expansion. Matter barely mattered in the early universe. Radiation energy dominated everything else so completely that ordinary matter acted like a minor contaminant in an ocean of light. During this radiation-dominated era, light pressure controlled cosmic expansion more than gravity from matter. Photons carried most of the universe's energy and momentum. Matter particles went along for the ride. This period lasted until the universe was about 50,000 years old. Only then did matter density finally catch up to radiation density as expansion diluted the light energy faster than it diluted matter. The transition from radiation dominance to matter dominance set the stage for everything that came after, including the formation of the first atoms. Free electrons turned the early universe into nature's ultimate pinball machine. These charged particles scattered light in every direction, making straight-line travel impossible for any photon. This process, called Thomson's scattering, created complete opacity throughout space. Light couldn't travel more than a tiny distance before hitting another electron and bouncing off in a random direction. Think of trying to see through a dense snowstorm where every snowflake is a mirror. Light bounced endlessly between electrons, making the universe act like the inside of a light bulb filament. Thomson's scattering maintained perfect thermal equilibrium by constantly mixing light and matter until atoms finally formed. The early universe was almost perfectly smooth. Density variations were incredibly tiny, less than 1 part in 100,000. This near-perfect uniformity seems impossible given the complexity we see today. Before gravity had time to create clumps and clusters, cosmic expansion kept everything evenly distributed. Matter spread uniformly throughout space like cream mixing perfectly into coffee. These smooth initial conditions were essential for later structure formation. If the early universe had been too lumpy, gravity would have created black holes instead of stars in galaxies. The slight imperfections that did exist became the seeds for everything we see in the modern cosmos. Nuclear fusion reactions created the universe's first heavy elements during its earliest minutes. But this element-building phase couldn't last forever. As expansion cooled the cosmic furnace, nuclear reactions simply stopped working. Big Bang nucleosynthesis ended when temperatures dropped below the threshold needed to fuse atomic nuclei together. This happened when the universe was about 20 minutes old and had cooled to roughly 1 billion degrees. From that point forward, only stars would be able to create new elements. The universe locked in its primordial composition of roughly 75% hydrogen and 25% helium, plus tiny traces of other light elements. This nuclear shutdown preserved the cosmic microwave background's perfect thermal signature by eliminating additional energy sources. Everything changed when matter density overtook radiation density. This cosmic transition happened gradually over thousands of years, but its effects transformed the universe's future completely. During the radiation era, pressure from light prevented matter from clumping together under gravity. Once matter took charge, gravitational collapse could begin forming the first cosmic structures. This transition occurred when the universe was about 50,000 years old. From that moment forward, matter controlled cosmic evolution while radiation became a background influence. The matter-dominated era made possible everything from the first stars to the formation of galaxies, planets, and ultimately life itself. The ratio of matter particles to light particles determined the universe's ultimate composition. Scientists call this baryon loading, which measures how much ordinary matter exists compared to the number of photons filling space. This ratio got locked in during the first few minutes after the Big Bang. For every billion photons in the cosmic microwave background, only 1 proton exists in the visible universe today. That tiny fraction of matter compared to radiation explains why space seems so empty. The universe contains vastly more leftover light than it does stars, planets, and everything else we can see. Baryon loading determined not just how much matter exists, but how it would eventually organize into cosmic structures. Entropy measures the amount of disorder in any system. During cosmic expansion, the total entropy per photon remained perfectly constant, following one of physics' most fundamental conservation laws. This entropy conservation meant that even as the universe expanded and cooled dramatically, it preserved perfect memory of its initial thermal state. The disorder couldn't increase or decrease during expansion. Entropy conservation explains why the cosmic microwave background maintains its perfect thermal signature after nearly 14 billion years. The expansion preserved the primordial thermal fingerprint exactly. This conservation law connects the universe's current state directly to its moment of origin, making the cosmic microwave background our most reliable witness to creation itself. What happens when the universe cools enough for chemistry to begin? For hundreds of thousands of years, space was too hot for atoms to exist. Then everything changed in a cosmic instant. Hydrogen recombination started when temperatures dropped low enough for protons and electrons to stick together. This wasn't really recombination since atoms had never existed before. Scientists just gave it that name because electrons were combining with nuclei for the first time. The process began when cosmic temperatures fell to about 3,000 degrees Kelvin. That's still hot enough to melt copper, but cool enough for the simplest atoms to survive without immediately getting ripped apart again. This temperature threshold marked the beginning of the universe's transition from a sea of charged particles to a cosmos filled with neutral atoms. How do you predict when atoms will form in a cooling universe? Scientists use something called the Saha equation, which works like a cosmic recipe that tells you the exact balance between atoms and free particles at any given temperature and density. This equation describes ionization equilibrium, which means the perfect balance between atoms forming and atoms getting destroyed by heat. Think of it like a tug of war between cooling, which helps atoms stick together, and leftover heat, which tries to tear them apart. The Saha equation showed that recombination wouldn't happen gradually. Instead, atoms would form in a sudden cascade once temperatures dropped just below the critical threshold. This statistical relationship lets scientists predict exactly when and how the cosmic microwave background would be released into free space. Free electrons had been the universe's light-blocking agents for hundreds of thousands of years, but atomic formation made most of them vanish from the cosmic scene almost overnight. When electrons bound to protons to form hydrogen atoms, the number of free electrons dropped by roughly 90% in just a few thousand years. These particles could no longer scatter light because they were now locked inside neutral atoms. Picture a crowded room where people constantly bump into a bouncing ball. Suddenly, most people sit down and stop moving. The ball can finally travel in straight lines across the room. This dramatic reduction in free electrons set the stage for the universe's first moment of optical transparency. The cosmic fog didn't lift gradually like morning mist. Instead, the universe's opacity dropped catastrophically as Thomson scattering suddenly became ineffective throughout space. Thomson scattering requires free electrons to work. When those electrons got locked inside atoms, they could no longer redirect light in random directions. The scattering cross-section collapsed almost to zero. This opacity crash happened because bound electrons behave completely differently from free ones. Free electrons scatter light at any wavelength, but bound electrons only interact with very specific colors of light. The universe transformed from completely opaque to nearly perfectly transparent in less than 100,000 years of cosmic time. Imagine the last moment when light bounced off matter before traveling freely forever. That moment defines a spherical surface surrounding us at a specific distance in every direction. Scientists call this the surface of last scattering, even though it's not really a surface you could touch. It's more like the edge of visibility, the farthest back in time we can see using light. Every photon in the cosmic microwave background scattered off an electron for the final time at this cosmic boundary. After that last collision, these photons began their billion-year journey toward our detectors. This surface represents the universe's transition from opacity to transparency, preserved as a spherical shell in space-time. Before atoms formed, light couldn't travel very far without hitting something. Scientists measure this distance as the mean free path, which tells you how far a typical photon could go before colliding with a free electron. During the opaque era, this distance was incredibly tiny compared to the size of the universe. Photons got scattered every few meters, making long-distance travel impossible. But when recombination removed most free electrons, the mean free path suddenly became comparable to the entire size of the observable universe. Light could finally travel from one side of the cosmos to the other without interruption. This transition from tiny mean free path to cosmic scale mean free path enabled the cosmic microwave background to begin its journey to Earth. For the universe's first few 100,000 years, matter and light were married in perfect thermal equilibrium. They shared energy constantly and maintained identical temperatures everywhere. Decoupling shattered this relationship permanently. Once electrons became bound in atoms, matter and radiation stopped exchanging energy efficiently. They began evolving along separate paths for the first time in cosmic history. Matter could now cool faster than radiation because it no longer had to maintain energy balance with photons. Meanwhile, radiation preserved its thermal signature while expanding and redshifting through space. This cosmic divorce allowed matter to begin gravitational collapse, while radiation became the fossil record we observe today. When we observe the cosmic microwave background, we're looking at the inside surface of a gigantic sphere. This surface of last scattering forms a complete bubble around us in three-dimensional space. The CMB photons we detect were all emitted from this spherical shell at roughly the same cosmic time. Different directions in the sky correspond to different locations on this ancient surface. We can map temperature variations across the sphere, just like cartographers map features on Earth's surface. The entire cosmic microwave background represents a complete spherical photograph of the early universe. This three-dimensional shell preserves a snapshot of cosmic conditions from 380,000 years after the Big Bang. Recombination didn't happen everywhere at exactly the same cosmic time. The redshift associated with this process tells us how much the universe expanded while atoms were forming. Scientists use recombination redshift as a precise ruler for measuring cosmic expansion. The value is approximately 1,100, which means the universe has expanded by that factor since atoms first formed. This stretching factor explains why the cosmic microwave background appears as microwaves today instead of visible light. The original visible and infrared radiation got stretched to much longer wavelengths by universal expansion. Recombination redshift provides one of our most accurate measurements of how much the universe has grown since its early transparent epoch. Not every cosmic microwave background photon was released at exactly the same moment. The visibility function describes the probability that a photon was emitted at any given time during the recombination process. This function shows that most photons were released during a relatively narrow window of cosmic time. The peak occurs at 380,000 years after the Big Bang, but the process had a characteristic width of several thousand years. Think of it like a bell curve showing when most students finish an exam. Some finish early, some late, but most complete their work around the same time. The visibility function explains why the cosmic microwave background has such a sharp boundary in cosmic time, rather than being spread out over millions of years. Atoms can only form and survive below a specific temperature threshold. Scientists call this the freeze-out temperature because it's like the freezing point for atomic formation. The freeze-out temperature for hydrogen atoms is approximately 3,000 degrees Kelvin. Below this temperature, electrons have low enough energy to get captured and held by protons. Above this temperature, thermal motion tears atoms apart faster than they can form. This critical temperature depends on both the universe's expansion rate and its density at the time of recombination. The relationship between temperature, time, and cosmic age follows precise physical laws. Freeze-out temperature marks the boundary between the ionized and neutral epochs in cosmic evolution. Recombination wasn't 100% efficient. Even after atoms formed throughout the universe, a small fraction of electrons remained free and continued scattering cosmic microwave background photons. This residual ionization amounts to roughly 10% of the original free electron population. While most electrons got bound into atoms, this leftover population still had measurable effects on the radiation we observe. These remaining free electrons created subtle distortions in the cosmic microwave background spectrum and polarization patterns. They also enabled later reionization when the first stars began shining. Residual ionization connects the cosmic microwave background era to later epochs of cosmic evolution and structure formation. Every hot object in the universe follows the same mathematical rule when it glows. Scientists discovered this pattern over a century ago and named it the Planck curve, after physicist Max Planck, who first figured out the equation. This curve tells you exactly how much light gets emitted at each wavelength for any object at any temperature. It's like nature's universal recipe for thermal radiation. No exceptions are known anywhere in the universe. The cosmic microwave background follows this curve with extremely high precision. When scientists plot the intensity of cosmic background radiation at different frequencies, they get a textbook-perfect Planck distribution. This mathematical perfection suggests the early universe achieved complete thermal equilibrium before atoms formed and light began traveling freely. How accurately can you measure the temperature of space itself? The PHIROS instrument aboard the Kui satellite achieved measurement precision that seemed impossible just decades earlier. PHIROS stands for Far Infrared Absolute Spectrophotometer, which means it could measure the exact amount of energy in cosmic background radiation at hundreds of different wavelengths simultaneously. The data points lined up on a perfect theoretical curve with no detectable deviations. This measurement became one of the most precise confirmations of blackbody radiation ever achieved. The cosmic microwave background spectrum matched theoretical predictions to within the measurement uncertainties of the instruments themselves. Yes, PHIROS showed that the universe's thermal radiation represents an extraordinarily perfect blackbody spectrum found anywhere in nature. Hot objects glow brightest at specific wavelengths that depend entirely on their temperature. This relationship, called Wien's displacement law, works like a cosmic thermometer that can measure the temperature of anything that glows. The rule is simple. Hotter objects emit their brightest light at shorter wavelengths, while cooler objects peak at longer wavelengths. A red-hot iron bar glows brightest in red light, while the sun peaks in yellow-green. For the cosmic microwave background, the peak wavelength occurs at about 1.9 millimeters. Wien's law tells us this corresponds to a temperature of exactly 2.725 degrees above absolute zero. This wavelength-temperature relationship provides an independent way to measure cosmic temperature that perfectly matches direct thermometer readings of space. The cosmic microwave background earned its name because it glows brightest in the same frequency range used by microwave ovens. This isn't a coincidence. Both involve electromagnetic radiation with wavelengths measured in millimeters. At the universe's current temperature of 2.7 degrees above absolute zero, thermal radiation peaks in the microwave portion of the electromagnetic spectrum. This puts cosmic background radiation between radio waves and infrared light on the energy scale. Microwave frequencies penetrate Earth's atmosphere easily, making ground-based detection possible. If cosmic expansion had stretched this radiation to different wavelengths, we might never have discovered it from our planet's surface. The microwave frequency range makes the cosmic background radiation detectable with relatively simple radio telescopes and sensitive receivers. Every blackbody radiator follows an ironclad rule about total energy output. The Stefan-Boltzmann law states that total radiated power increases as the fourth power of temperature, meaning small temperature changes create huge energy differences. This law explains why stars are so much brighter than planets. A star's surface temperature of thousands of degrees produces vastly more energy per square meter than a planet's surface at hundreds of degrees. For the cosmic microwave background, this relationship determines the total energy density of radiation throughout all of space. The energy density equals about 400 million photons per cubic meter of empty space. The Stefan-Boltzmann law connects cosmic temperature measurements to the total amount of radiant energy filling the universe. Photons possess a unique characteristic that allows perfect blackbody radiation to exist. Unlike matter particles, photons have zero chemical potential, meaning they can be created or destroyed without conserving particle number. Chemical potential measures how much energy it costs to add one more particle to a system. For photons, this cost equals zero because electromagnetic radiation adjusts freely to maintain perfect thermal equilibrium with its surroundings. This property enabled the early universe to maintain perfect thermal balance between matter and radiation for hundreds of thousands of years. Photons could be absorbed and re-emitted freely without changing the system's fundamental character. Zero chemical potential explains why the cosmic microwave background achieved such perfect blackbody characteristics during the thermal equilibrium epoch. Scientists have measured the cosmic microwave background temperature with extraordinary precision. The current best measurement gives 2.72548 degrees Kelvin above absolute zero, accurate to within a few thousandths of a degree. This represents one of the most precisely determined constants in all of cosmology. The measurement uncertainty is smaller than the temperature difference between your bedroom and hallway on a typical day. Multiple independent satellite missions have confirmed this temperature to incredible accuracy. The consistency of measurements from different instruments and techniques validates our understanding of cosmic thermal radiation. Precise temperature measurement provides a fundamental standard for cosmic microwave background studies and cosmological parameter determination. Thermodynamic equilibrium means every part of a system maintains exactly the same temperature and energy distribution. The early universe achieved this perfect balance throughout all of space for hundreds of thousands of years. In equilibrium, photons follow Bose-Einstein statistics, which describes how particles with zero mass and spin distribute themselves across different energy levels. This creates the characteristic curved shape of blackbody radiation spectra. The cosmic microwave background preserves this perfect statistical distribution even after nearly 14 billion years of cosmic expansion. Expansion stretched the wavelengths but preserved the fundamental equilibrium character of the radiation. Thermodynamic equilibrium explains both the perfect blackbody spectrum and the statistical properties of cosmic microwave background fluctuations. Could anything disturb the cosmic microwave background's perfect blackbody spectrum? Scientists actively search for spectral distortions that would reveal non-equilibrium processes in the early universe. Spectral distortions are tiny deviations from the perfect Planck curve that could be caused by energy injection matter interactions or exotic physics during cosmic history. These distortions would appear as subtle changes in the shape of the spectrum. Current measurements show no detectable spectral distortions within instrumental limits. The cosmic microwave background maintains its perfect blackbody character to incredible precision across all measured frequencies. The absence of spectral distortions constrains models of early universe physics and confirms that thermal equilibrium persisted until atoms formed. Comptonization occurs when low-energy photons scatter off high-energy electrons and gain energy in the process. This interaction can distort blackbody spectra by transferring energy from hot electrons to cooler radiation. The process works like cosmic pinball, where energetic electrons act as fast-moving flippers that speed up the photon balls they hit. Multiple scatterings gradually shift the entire spectrum toward higher energies and shorter wavelengths. Scientists search for comptonization signatures in the cosmic microwave background that would indicate hot electron populations during or after recombination. Such signatures would reveal early star formation or other high-energy processes. Comptonization studies help distinguish between different models of cosmic reionization and early structure formation in the universe. Brightness temperature provides a way to convert observed radiation intensity into equivalent blackbody temperature. This measurement technique works by asking, what temperature would a perfect blackbody need to produce this observed brightness? The method assumes the radiation follows a perfect Planck spectrum, then uses the observed intensity to calculate the corresponding temperature. For true blackbody sources, brightness temperature equals the actual physical temperature exactly. Brightness temperature measurements of the cosmic microwave background give about 2.725 degrees Kelvin in every direction across the sky. This confirms both the thermal nature of the radiation and its perfect isotropy at large angular scales. Brightness temperature provides the standard method for measuring cosmic microwave background temperature and mapping its tiny fluctuations across the celestial sphere. The CMB satellite changed everything in 1992. Scientists expected to find perfect uniform temperature across the entire cosmic microwave background. Instead, they discovered something extraordinary. Tiny temperature variations appeared everywhere they looked. These differences measured only about 1 part in 100,000, making them almost impossibly small to detect. Imagine trying to measure the difference between 100.0000 degrees and 100.00001 degrees. These minuscule temperature fluctuations represented the first direct evidence that the early universe wasn't perfectly smooth. The discovery earned a Nobel Prize because it solved one of cosmology's biggest mysteries. Without these cosmic imperfections, the universe today would be empty and lifeless, containing nothing but smooth gas expanding forever through space. Dense regions of matter in the early universe acted like cosmic valleys. Just as water flows into low places on Earth, matter naturally collected in areas where gravity was slightly stronger than average. These density fluctuations during recombination showed up as temperature variations in the cosmic microwave background. Regions with more matter appeared as warmer or cooler spots, depending on the specific physical processes involved. The connection works because matter and radiation were still coupled together when atoms first formed. Where matter clumped together, radiation carried the signature of that gravitational interaction. Matter density differences of just 0.001% created the temperature variations that CMB detected across the ancient sky. Light loses energy when it climbs out of gravitational valleys. This happens because gravity literally pulls on photons as they try to escape from regions of high matter density. Scientists call these dense regions gravitational wells, like invisible holes in space that trap both matter and energy. When cosmic microwave background photons emerged from these wells, they arrived at our detectors with slightly less energy than photons from emptier regions. Less energetic photons appear cooler in temperature measurements. This creates cold spots in the cosmic microwave background map that directly trace where matter was clumped together during recombination. Gravitational wells transformed tiny matter over densities into observable temperature patterns that span the entire sky. Why do some regions of the cosmic microwave background appear hotter or cooler than others? The answer lies in gravitational potential differences that existed during the recombination era. The Sachs-Wolf effect describes how photons gain or lose energy depending on the gravitational environment they originated from. Photons climbing out of gravitational wells become redshifted and appear cooler, while photons from low-density regions maintain higher energies. This effect acts like a cosmic fossil record, preserving information about matter distribution from 380,000 years after the Big Bang. Each temperature fluctuation tells us about gravitational conditions in a specific region of the early universe. The Sachs-Wolf effect provides the primary mechanism connecting primordial density variations to observable temperature differences in today's cosmic microwave background. Every galaxy cluster in the modern universe traces back to tiny density fluctuations visible in the cosmic microwave background. These temperature variations mark the locations where cosmic structure formation began. The process worked like cosmic urban planning. Slightly denser regions attracted more matter over billions of years, eventually becoming the scaffolding for galaxy formation. Meanwhile, underdense regions became the empty voids we observe between galaxy clusters today. Computer simulations can trace this evolution from cosmic microwave background fluctuations to modern large-scale structure. The tiny temperature variations act as blueprints for everything we see in today's universe. Structure formation seeds explain why galaxies aren't randomly scattered through space, but instead form a cosmic web of filaments and clusters. Individual directions across the sky show clear temperature variations in the cosmic microwave background. But when you average all these variations together, they cancel out perfectly to produce zero net deviation. This property is called statistical isotropy, meaning the universe has no preferred directions even though it's clearly not smooth on smaller scales. It's like flipping coins where individual flips vary but large numbers of flips average to 50% heads. The random distribution of hot and cold spots follows no geometric pattern across the sky. North, south, east, and west all show the same statistical properties when averaged over large enough regions. Statistical isotropy confirms that cosmic structure grew from random quantum fluctuations rather than from any organized initial conditions. Temperature fluctuations in the cosmic microwave background follow a beautiful mathematical pattern. When scientists plot the frequency of different temperature values, they get a perfect bell-shaped curve. This distribution is called Gaussian, named after mathematician Carl Friedrich Gauss, who first described it. Gaussian patterns appear in nature whenever random processes create variations around a central average value. The cosmic microwave background shows Gaussian statistics because the primordial density fluctuations originated from quantum mechanical processes. Quantum uncertainty naturally creates random variations that follow Gaussian distributions. Gaussian fluctuations prove that cosmic structure formation began with truly random seeds rather than organized patterns or special initial conditions. How do you quantify the strength of temperature variations across the entire cosmic microwave background? Scientists use a statistical measure called RMS fluctuations, which captures the typical size of temperature differences. RMS stands for root mean square, which means you square all the temperature differences, average them, then take the square root. This mathematical process gives you a single number that characterizes how rough or smooth the cosmic microwave background appears. The RMS temperature fluctuation measures approximately 18 microkelvin across the sky. That incredibly small number represents the strength of density variations that seeded all cosmic structure formation. RMS fluctuations provide a precise way to compare theoretical predictions with observational measurements of cosmic microwave background anisotropy. Light can only travel so far during any given time period, even in an expanding universe. This fundamental speed limit determined the maximum size of connected regions during the recombination era. Scientists call this distance scale the horizon scale. Representing the farthest apart two regions could be while still maintaining physical communication. Beyond this distance, different parts of the universe evolved independently without coordinating their properties. The horizon scale during recombination corresponds to about 1 degree of angular size in today's cosmic microwave background observations. This sets the characteristic scale for the largest temperature variations we observe. Horizon scale physics explains why cosmic microwave background fluctuations show specific angular sizes rather than variations at all possible scales. The ultimate source of cosmic microwave background fluctuations traces back to the universe's earliest moments. These primordial perturbations originated during cosmic inflation, when quantum fluctuations got stretched to macroscopic sizes. During inflation, tiny quantum mechanical uncertainties expanded exponentially to become the density variations visible in the cosmic microwave background. This process transformed microscopic physics into cosmic architecture. The statistical properties of these primordial perturbations match exactly what we observe in cosmic microwave background temperature maps. The connection provides strong evidence that inflation really happened in the early universe. Primordial perturbations represent the deepest link between quantum mechanics and cosmic structure, connecting the smallest and largest scales in physics through observable temperature fluctuations. Sound waves filled the early universe long before the first atom formed. But these weren't ordinary sound waves traveling through air. They were pressure oscillations in a hot plasma made of charged particles and light. Scientists call these baryon acoustic oscillations, which means sound waves involving ordinary matter particles. The baryon part refers to protons and neutrons, while acoustic means they behaved exactly like sound waves in any other medium. Gravity tried to pull matter together into clumps, while radiation pressure pushed back to keep things spread apart. This cosmic tug of war created oscillations that rippled through space like sound waves through water. These primordial sound waves left their signature permanently imprinted in the cosmic microwave background temperature patterns we observe today. How far can sound waves travel in a finite amount of time? In the early universe, sound had roughly 380,000 years to propagate before atoms formed and stopped the oscillations completely. Scientists call this distance the sound horizon, representing the maximum distance that acoustic signals could travel during the pre-recombination era. Think of it like the furthest you could hear thunder after seeing lightning. The sound horizon corresponds to about 150 million light-years in today's universe, after accounting for cosmic expansion. This distance sets the characteristic scale for the largest temperature fluctuations visible in the cosmic microwave background. The sound horizon explains why cosmic microwave background variations show specific angular sizes rather than being random at all scales. Two opposing forces waged war in the early universe's plasma. Gravity pulled matter inward, trying to create dense clumps. Radiation pressure pushed outward, trying to smooth everything back out. This compression process worked like a cosmic accordion. When gravity compressed a region, radiation pressure built up until it explosively pushed the matter back out. Then gravity would pull it in again, creating endless cycles of compression and expansion. Each cycle took thousands of years to complete, with the plasma oscillating back and forth around equilibrium positions. Different regions oscillated at different phases, some compressing while others expanded. These compression battles created the pressure waves that we observe as acoustic peaks in the cosmic microwave background power spectrum. Before atoms formed, photons and matter particles were locked together in a single flowing substance. Thomson's scattering made free electrons and light interact so strongly that they couldn't move independently. Scientists call this mixture the photon-baryon fluid, meaning light and ordinary matter behaved like one unified liquid. When gravity pulled on the matter, it dragged the light along too. When radiation pressure pushed, it moved both components together. This tight coupling created collective motion throughout the cosmic plasma. Individual particles couldn't go their own way because electromagnetic forces kept everything moving as a coordinated whole. The photon-baryon fluid enabled sound waves to propagate efficiently through the early universe until atomic formation broke the coupling. Some regions of the early universe reached maximum compression exactly when atoms started forming. These areas showed up as the hottest spots in the cosmic microwave background because compression heats up any gas or plasma. This creates the first acoustic peak in cosmic microwave background measurements, representing the strongest temperature fluctuations at a specific angular scale. The peak occurs at about 1 degree across the sky in today's observations. Maximum compression happened because these regions were at the right phase in their oscillation cycle when recombination froze the acoustic waves. They got caught with their matter squeezed to the highest possible density. The first peak dominates cosmic microwave background temperature maps because compression naturally creates the strongest observable signals. Other regions reached maximum expansion when atoms formed, creating the second acoustic peak in cosmic microwave background observations. These areas show smaller temperature fluctuations because expansion tends to cool plasma down. The second peak appears at smaller angular scales and with lower amplitude compared to the first peak. This creates a characteristic pattern of alternating strong and weak signals in the cosmic microwave background power spectrum. Maximum expansion regions were caught at the opposite phase of their oscillation cycle during recombination. They had just finished pushing their matter to the lowest possible density when acoustic waves suddenly stopped. The second peak provides crucial information about the balance between matter and radiation in the early universe. Cosmic microwave background peaks follow the same mathematical pattern as musical harmonics. Just like a piano string produces a fundamental tone plus higher frequency overtones, acoustic oscillations created a fundamental scale plus smaller scale harmonics. This harmonic series appears as a sequence of peaks in the cosmic microwave background power spectrum, with each peak occurring at a predictable angular scale. The pattern resembles the acoustic signature of a cosmic musical instrument. The fundamental frequency was set by the sound horizon scale, while higher harmonics correspond to shorter sound wave cycles that could fit within that distance. Each harmonic peak tells us about different aspects of early universe physics. Musical harmony in the cosmos provides one of the most elegant confirmations of Big Bang cosmology and acoustic oscillation theory. Acoustic oscillations couldn't continue indefinitely at smaller and smaller scales. Physical processes like diffusion and viscosity gradually dampened the wave amplitudes, creating what scientists call the damping tail. At very small scales, the cosmic plasma began acting more like a viscous fluid than a perfect oscillating medium. Particle collisions created friction that absorbed acoustic energy and converted it into random thermal motion. This damping occurs beyond about 10 arcminutes in angular scale on the cosmic microwave background. Smaller fluctuations get progressively weaker because the acoustic waves couldn't maintain their strength at these scales. The damping tail marks the transition from coherent acoustic oscillations to random thermal fluctuations in early universe physics. How do you analyze temperature patterns spread across the entire spherical sky? Scientists use a mathematical technique called multiple expansion, which breaks complex patterns into simpler geometric components. This method works like analyzing a musical chord by separating it into individual notes. The cosmic microwave background's complex temperature map gets decomposed into spherical harmonics, each corresponding to different angular scales and geometric patterns. Each multiple mode captures fluctuations at a specific angular size, from the largest possible scale down to the resolution limit of the measurements. Lower multiple numbers correspond to larger angular scales, while higher numbers represent smaller features. Multiple expansion transforms cosmic microwave background observations into the power spectrum format that reveals acoustic peak structure. The power spectrum shows how much temperature fluctuation exists at each angular scale across the cosmic microwave background. It's like a cosmic frequency analysis that reveals the strength of patterns at different sizes. Each multiple mode contributes a specific amount of power to the overall temperature variations. When you plot power versus multiple number, the acoustic peaks emerge as clear bumps at predictable locations. The power spectrum format allows precise comparison between theoretical predictions and observational data. The peak heights, positions, and shapes encode detailed information about cosmic parameters and early universe physics. Power spectrum analysis transformed cosmic microwave background studies from qualitative pattern recognition into quantitative precision cosmology. During the first 380,000 years after the Big Bang, photons and ordinary matter existed in a state called tight coupling. Thomson scattering made the interaction between light and electrons so strong that they couldn't separate or move independently. This tight coupling created a unified cosmic medium where electromagnetic forces linked light and matter into a single responsive fluid. Any disturbance affected both components simultaneously, enabling collective acoustic oscillations. The coupling strength determined how efficiently sound waves could propagate and how much they would be dampened by particle interactions. Perfect coupling would allow indefinite propagation, while loose coupling would kill the oscillations quickly. Tight coupling maintained acoustic wave coherence until recombination suddenly broke the electromagnetic bonds between photons and matter. Cosmic plasma oscillations didn't stop exactly at their equilibrium positions. Instead, momentum carried the flowing matter past the balance point, creating velocity overshoot effects that influenced the acoustic peak structure. This inertial overshoot works like a pendulum that swings past its rest position because it still has kinetic energy from the previous motion. The cosmic plasma's momentum made it compress more than equilibrium would predict. The overshoot effect creates phase relationships between density fluctuations and velocity patterns that determine the relative heights of different acoustic peaks in the power spectrum. Velocity overshoot explains the detailed shape and amplitude ratios of cosmic microwave background acoustic peaks observed in precision measurements. Light waves vibrate as they travel through space, but most people don't realize these vibrations can carry extra information beyond just brightness and color. When free electrons scatter incoming light, they create polarization patterns that reveal details invisible in temperature measurements alone. Thomson scattering naturally produces polarized light when photons bounce off free electrons. This happens because electrons preferentially scatter light in certain directions depending on the original vibration direction of the incoming radiation. The process works like sunlight reflecting off water. Scattered light becomes partially polarized, meaning its electromagnetic waves vibrate more in some directions than others. This creates a subtle but measurable signature in the scattered radiation. Thomson scattering in the early universe generated polarization signals that complement temperature information in the cosmic microwave background. Not all temperature variations in the cosmic microwave background can produce polarization signals. Only specific geometric patterns of hot and cold regions generate polarized light when electrons scatter the radiation. Scientists call the required pattern quadrupole anisotropy, which means temperature variations that change in fourfold symmetry around any given point. Imagine a four-leaf clover pattern, where opposite leaves are hot while the other two are cold. This quadrupole pattern is essential because Thomson scattering only creates polarization when incoming light has different intensities from perpendicular directions. Uniform temperature or simple hot-cold contrasts cannot generate polarized, scattered light. Quadrupole temperature fluctuations in the early universe provided the geometric conditions necessary for Thomson scattering to create observable linear polarization. Cosmic microwave background polarization comes in two distinct geometric types, like left-handed and right-handed patterns in nature. The first type, called E-mode polarization, creates smooth swirling patterns without any twisting or curl. E-mode patterns look like flow lines around high and low pressure regions on a weather map. The polarization vectors point radially toward or away from temperature extremes, creating organized patterns that scientists can map and analyze. These curl-free patterns originate directly from the density fluctuations that created temperature variations during recombination. When matter clumped together or spread apart, it generated the quadrupole patterns needed for E-mode polarization production. E-mode polarization provides independent confirmation of cosmic microwave background temperature measurements and reveals additional details about early universe matter distribution. The second type of cosmic microwave background polarization creates patterns with curl and twist, like whirlpools in a flowing river. Scientists call these B-mode patterns because they behave mathematically like magnetic field lines. B-mode polarization cannot be produced by ordinary density fluctuations during recombination. Instead, these twisted patterns require either primordial gravitational waves from cosmic inflation or gravitational lensing effects that distort the polarization as light travels to us. Detecting B-mode signals would provide the first direct evidence for gravitational waves from the universe's earliest moments. These ripples in space-time itself would represent the ultimate confirmation of inflationary cosmology. B-mode polarization hunting has become one of the most challenging and important frontiers in cosmic microwave background research. After atoms formed and the cosmic microwave background was released, the universe entered a dark period lasting hundreds of millions of years. No stars existed yet to light up space. Then everything changed when the first massive stars ignited. This epoch of reionization began when the earliest stars and galaxies produced enough ultraviolet radiation to strip electrons away from atoms throughout space. The process reversed recombination, turning neutral atoms back into free ions and electrons. Reionization didn't happen all at once. It proceeded in patches as star-forming regions created expanding bubbles of ionized gas. These bubbles gradually merged until most of the universe became ionized again. The epoch of reionization created a second population of free electrons that could scatter cosmic microwave background photons one more time before they reached our telescopes. How much did reionization affect cosmic microwave background photons during their final journey to Earth? Scientists measure this using a parameter called tau, which quantifies the average number of scattering events each photon experienced. Tau works like a measure of fog thickness. A tau value of 0 means perfectly clear conditions with no scattering, while larger tau values indicate progressively foggier conditions where photons get scattered more frequently. Current measurements give a tau value of approximately 0.05 for reionization scattering. This means the typical cosmic microwave background photon had about a 5% chance of scattering off a free electron during reionization. The tau parameter connects cosmic microwave background observations to the timing and efficiency of the first star formation in cosmic history. Reionization created a new population of free electrons that could scatter cosmic microwave background radiation and generate fresh polarization signals. These new signals appeared at much larger angular scales than the original recombination polarization. Large-scale polarization patterns extend across several degrees on the sky, corresponding to the sizes of reionization bubbles when the first stars began shining. This revival of polarization provides a unique window into cosmic dawn. The large-scale patterns differ fundamentally from small-scale recombination polarization because they trace the patchy structure of early star formation rather than primordial density fluctuations. Large-scale polarization measurements help scientists understand when reionization occurred and how quickly the first stars ionized their surrounding gas. What fraction of cosmic microwave background intensity gets converted into polarization during scattering events? The polarization fraction measures this efficiency and tells us about the physical conditions during scattering epochs. Polarization fraction equals the polarized intensity divided by the total intensity, typically expressed as a percentage. Higher fractions indicate more efficient polarization production, while lower values suggest weaker scattering conditions. For cosmic microwave background radiation, polarization fractions are quite small, typically less than 10% of the temperature fluctuation amplitude. This reflects the relatively weak polarization efficiency of Thomson's scattering under cosmic conditions. Polarization fraction measurements provide quantitative tests of scattering physics and help distinguish between different models of recombination and reionization. Even with perfect instruments and infinite observing time, cosmic microwave background measurements face an absolute limit called cosmic variance. This represents the statistical uncertainty that comes from observing only one realization of cosmic evolution. Cosmic variance exists because we can observe only our single universe, not an ensemble of many possible universes with different random initial conditions. This creates irreducible statistical uncertainty in measurements of large-scale patterns. The effect becomes most important for measurements of large angular scales, where only a few independent samples exist across the entire sky. Small-scale measurements have many independent samples and therefore smaller cosmic variance. Cosmic variance sets the ultimate precision limit for cosmic microwave background cosmology and determines which questions can be answered definitively with observations. Our Milky Way galaxy produces its own polarized microwave radiation that can contaminate cosmic microwave background measurements. This foreground contamination comes primarily from interstellar dust grains and high-energy electrons in galactic magnetic fields. Dust particles in our galaxy emit polarized thermal radiation when they align with magnetic field lines. Meanwhile, relativistic electrons spiraling around magnetic fields create synchrotron radiation that also shows strong polarization. These galactic foregrounds often produce stronger polarization signals than the cosmic microwave background itself, especially at low frequencies and along the galactic plane. Separating cosmic signals from galactic contamination requires sophisticated analysis techniques. Foreground contamination represents the primary obstacle to precise cosmic microwave background polarization measurements and B-mode detection. Temperature and polarization measurements in the cosmic microwave background are not independent random signals. Instead, they show cross-correlation patterns that provide additional cosmological information beyond what either measurement can reveal alone. Cross-correlation analysis compares temperature and polarization maps to find locations where both signals are stronger or weaker than average. These correlations arise because both signals originated from the same underlying density fluctuations during recombination. The correlation patterns break degeneracies that limit the precision of cosmological parameter measurements. When temperature and polarization data agree on parameter values, scientists gain much higher confidence in their results. Cross-correlation between temperature and polarization signals has enabled precision cosmology measurements that achieve unprecedented accuracy in determining fundamental cosmic parameters. Scientists can now describe the entire universe using just 6 fundamental numbers: This seems almost impossible given the cosmic complexity we observe. Yet decades of cosmic microwave background measurements have proven this standard model works with remarkable precision. These 6 parameters control everything from the universe's age and size to the formation of galaxies and the abundance of chemical elements. They determine cosmic geometry, expansion history, and the balance between different types of matter and energy. The Standard Model represents one of science's greatest achievements in reducing cosmic complexity to essential mathematical relationships. Each parameter has been measured to percent-level accuracy using cosmic microwave background observations. 6 numbers provide a complete recipe for recreating our universe's properties from the Big Bang to the present day. Measuring how fast the universe expands right now requires connecting observations across vastly different distance scales. The Hubble constant quantifies this expansion rate, but different measurement methods have produced conflicting results for decades. Cosmic microwave background observations provide an independent way to measure cosmic expansion by analyzing the acoustic scale imprinted in temperature fluctuations. This method doesn't rely on distance ladder techniques that use nearby stars and supernovas. The acoustic approach gives a Hubble constant value of approximately 67 kilometers per second per megaparsec. This means space expands by 67 kilometers per second for every 3.26 million light-years of distance. Cosmic microwave background measurements offer a completely different pathway to cosmic expansion that bypasses potential systematic errors in local distance measurements. What fills the universe? Cosmic microwave background observations can weigh different types of matter with extraordinary precision by analyzing how acoustic peaks change height relative to each other. The ratio between ordinary matter and dark matter shows up clearly in the acoustic peak structure. Ordinary matter, made of protons and neutrons, comprises only about 5% of the universe's total mass energy content. Dark matter contributes roughly 27% of cosmic density, making it over 5 times more abundant than the matter that forms stars, planets, and everything else we can see directly. Matter density measurements from acoustic peaks provide the most precise inventory of cosmic ingredients available to modern cosmology. 2/3 of the universe consists of something that pushes space apart rather than pulling it together. Scientists call this dark energy, and it represents the most significant unsolved mystery in modern physics. Dark energy creates cosmic acceleration by exerting negative pressure throughout space, counteracting the attractive force of gravity on cosmic scales. This causes the expansion rate to speed up over time rather than slow down as expected. The cosmic microwave background constrains dark energy density through its effects on cosmic geometry and the growth of structure over billions of years. Current measurements suggest dark energy makes up approximately 68% of total cosmic density. Dark energy measurements reveal that our universe's fate will be determined by this mysterious component rather than by ordinary matter or even dark matter. Is space flat like a table, curved like a sphere, or saddle-shaped like a mountain pass? The cosmic microwave background provides a precise test of cosmic geometry by measuring characteristic angular scales in temperature fluctuations. Curvature affects how light travels across cosmic distances, changing the apparent size of acoustic peaks in the temperature-power spectrum. Flat geometry preserves angular relationships, while curved space distorts them predictably. Current measurements indicate the universe is geometrically flat to within measurement uncertainties. The curvature parameter differs from 0 by less than 1%, suggesting space extends infinitely without global curvature. Geometric flatness measurements confirm theoretical predictions from cosmic inflation and constrain models of cosmic evolution. Did primordial density fluctuations have the same strength at all size scales, or did larger structures start with stronger initial variations? The spectral index measures this scale dependence and provides crucial tests of cosmic inflation models. A spectral index of exactly 1 would mean equal fluctuation strength at all scales, while values less than 1 indicate weaker fluctuations at larger scales. Most inflation models predict spectral indices slightly below unity. Current cosmic microwave background measurements give a spectral index of approximately 0.96, confirming that large-scale fluctuations were indeed slightly weaker than small-scale ones during the primordial epoch. Spectral index measurements provide direct observational tests of quantum mechanical predictions for primordial fluctuation generation during cosmic inflation. Neutrinos have tiny masses that seemed negligible until scientists realized they could affect cosmic structure formation on the largest scales. These nearly massless particles create subtle signatures in cosmic microwave background observations. Massive neutrinos suppress the growth of cosmic structure because they move too fast to participate in gravitational collapse during early epochs. This creates measurable effects in both cosmic microwave background fluctuations and large-scale galaxy surveys. Current measurements constrain the sum of all neutrino masses to be less than about 0.12 electron volts. This represents one of the most precise limits on neutrino properties available from any experimental technique. Neutrino mass constraints demonstrate how cosmic microwave background observations can probe fundamental particle physics through cosmological effects. Primordial gravitational waves from cosmic inflation would create a distinctive signature in cosmic microwave background polarization patterns. The tensor-to-scalar ratio measures the strength of these gravitational wave fluctuations compared to ordinary density fluctuations. Detecting this ratio would provide the first direct evidence for gravitational waves from the universe's earliest moments and confirm that inflation involved energy scales approaching the Planck scale, where quantum gravity becomes important. Current upper limits constrain the tensor-to-scalar ratio to be less than 0.06, meaning primordial gravitational waves contribute less than 6% of the total fluctuation power in cosmic microwave background observations. Tensor-to-scalar ratio measurements represent the most ambitious goal in cosmic microwave background research and could transform our understanding of fundamental physics. What comes after current cosmic microwave background satellites? The CMB S4 project represents the next major advancement, combining ground-based and space-based observations to achieve unprecedented sensitivity and resolution. CMB S4 stands for Cosmic Microwave Background Stage 4, indicating it's the fourth generation of major cosmic microwave background experiments. This project will deploy thousands of ultra-sensitive detectors across multiple observatory sites. The improved sensitivity will enable detection of gravitational wave signatures, precise measurements of dark energy evolution, and constraints on exotic physics beyond the standard cosmological model. CMB S4 will push cosmic microwave background science into a new era where systematic uncertainties become more important than statistical noise in determining measurement precision. Modern cosmic microwave background measurements have achieved something unprecedented in cosmology: percent-level precision in determining fundamental cosmic parameters. This represents the maturation of cosmology from descriptive science to precision physical science. Precision cosmology means scientists can now test theoretical models with the same rigor applied to laboratory physics experiments. Competing theories can be definitively ruled out or confirmed based on high-precision observational tests. The combination of cosmic microwave background measurements with other cosmological probes has established the standard cosmological model as one of the most successful theories in all of physics. Precision cosmology opens new frontiers for testing fundamental physics, from quantum mechanics in the early universe to the nature of dark matter and dark energy.